Thank you.
Okay. Um, yeah, so this is a complete introduction. It is not going to get into anything deep. If you already know about artificial neural networks or deep learning, you're probably not going to learn anything new here. This is just to kind of give a background for what's going on. And I figured I might, in this audience, find people who know more than I do, and I wouldn't be surprised about that. Um, let's see if I can advance my slides. So first of all, what's traditional computing? I'm not even going to assume that you know what traditional computing is. But if you're not familiar with programming or algorithms, you probably know something about recipes or plans. And that is a program or a plan or a recipe or an algorithm is just a bunch of steps which, given input, produces a desired output. Generally, those steps are followed sequentially, but the program may specify, the program or plan or recipe or whatever can specify repeating steps or skipping steps or steps to take instead of other steps. So like for recipe, it might, if you're making, okay. Yeah, so like if you're making cookies, the recipe might say something like dollop the dough onto the cookie sheet in tablespoons, each 2 inches apart until the cookie sheet is full. That's an example of a repetition happening. The recipe might say, if you don't have buttermilk, you can use milk and lemon juice or something. That's an example of an alternative. There's just all these kinds of things that you recognize as recipes or plans are very, very much the same thing as you get with programming and algorithms. It's just steps to follow. They're generally sequential steps. The program can specify repeating, skipping, or alternatives. So Alan Turing, people were deciding exactly what does computing mean for quite a while. Alan Turing kind of formalized the idea in 1936. He came up with a model of computation which has since been called the Turing machine, and it basically just formalizes that idea that computation is this matter of following these steps, and you can take alternatives and you can repeat and things like that. So the Turing machine formalizes that idea. But of course, people also think of when they're computing mathematical formulas or functions or whatever, isn't that computing too? Well, yes, it is. And in fact, uh, for all effective purposes, anything that can be expressed as a calculation can be expressed as a computation with these steps and things, and vice versa. Um, Now we have functional languages where you actually just you can express an entire computer program just as mathematical formulas, basically. Um, this idea that anything you can do, you can express one way, you can express the other way, was formalized in something called the Church-Turing thesis. And that just says computing is computing, whether or not you're doing mathematical formulas or following these steps. It's all basically the same kind of thing. So that's what we've meant by computing up till now. Um, and what is a computer? Well, I should say that the first computers were people. There would be big rooms full of people, often women, who would just basically follow compute formulas and things, often for the military or something, and they were called computers. And then we started getting electronic digital computers, and in a traditional computer, you've got a CPU, which is a central processing unit. It fetches instructions from a memory. It sees what the instruction is supposed to do, decodes it, and executes it, does whatever it says. What it says is one of those things I said before. It's either a step to follow or an alternative. It tells you to take an alternative or repeat, etc. And as it does so, it may access or store data in a memory in order to do to do the operation and decide what the next instruction is to execute. Today's CPUs can execute about 1 billion instructions per second per thread. Now, today's CPUs also have many threads that can execute at one time, and I'm not going to go into what threads are about right now. But basically, each thread is one of these computations that's running. And by tying together many processors, we're currently striving to get to a level called exascale computing, which is basically 1 billion operations per second. And some will claim that we've reached that, we've attained that goal already. But all of this is still this same idea of just following these instructions and just this very step-by-step operational approach. So almost ever since that we've had this, Turing came up with this idea of Turing formalized this idea of computation, we've also considered what is intelligence. That is, can we actually make something intelligent out of a computer that's following steps like that? And how do we even know it's intelligent? What do we mean by intelligence? And I'm not going to really answer very many of those questions here, but I'll give you a little bit of history. Turing came up with this idea that just says, it basically just says, if you can't tell it's not a human, then it must be intelligent. The idea being that if there's some locked room somewhere and you're communicating with some entity inside the room over some electronic processor, for example, or a terminal or something, and it's communicating back with you and you cannot tell that it's not a human, then you must admit that it's intelligent. That's a little bit unsatisfying for a whole lot of reasons, but it was a good start. It was something that we could at least work with. But you can, for example, imagine that the thing in the room is so intelligent that we could easily tell that it's not a human that's coming up with all that intelligence. And does that mean it's not intelligent? I don't think so. So this whole idea of what's intelligent is you can go on and on about that, but I'm not going to spend too much time here. But except to say that it is an important question as to whether you can take something like a computer that follows all these very precise steps and come up with something that's intelligent. And there have been lots of examples. I mean, there's a very simple example that was made many years ago with even very simple computation called ELIZA, where it would just basically take sentences that you gave it and it would pretend to be a psychiatrist and toss them around and throw them back at you and try to get you to elucidate on them, basically. And at first glance, it could have been a human that was responding to you. It was not obvious until you started asking it a few questions and you noticed that everything was just a pattern that it was throwing back at you. There's a there's a thought experiment called the Chinese room, where, you know, if you've got an entity sitting in a room and it has some kind of book and this entity, let's say it's a human, doesn't understand Chinese at all. But you send Chinese symbols into the room, and this human has a book that it can look up Chinese symbols, and the book has a list of instructions that says, if these Chinese symbols come in, then you should send these Chinese symbols out the door. And so the human does that, And the person outside says, wow, this person must understand Chinese. It makes perfect sense. Well, the person doesn't understand Chinese at all. And that's very similar to what a computer would do. So is that really intelligence? Is it really understanding? There's lots of questions you can get into along those lines. Um, but the real point is, using this traditional form of computing, we really got hardly anywhere with artificial intelligence, with making anything that had the kinds of capabilities that humans had to understand what people were saying, to understand what it was seeing, to understand, or understand, of course, is a loaded word there, but to be able to react reasonably to those things in ways that would help us out. Um, and and along those lines, is writing a program the same thing as teaching a computer? I mean, writing a program is all these very precise steps. Is that what we think of as teaching? Um, I don't think I see teaching that way. And do we think of the computer as learning? Um, a, a child often learns a lot on its own by interacting with its environment, but a computer really doesn't have senses generally, and has very limited interaction with its environment. So I will just sort of skip forward. So okay, so Turing came up with this formal concept of computing, and I've already told you the kind of abbreviated forms of that. So is that kind of like what's happening in our brain? And the answer is no, not at all. I mean, there's nothing natural at all about this form of computing that I've been talking about. It just happened to be a fairly reasonable way to communicate between humans about what we want to get done. So a list of steps is easy for a human to follow. Um, this idea of alternatives, etc. It's really just a language construct for having humans communicate with each other, or have humans communicate with a machine. Um, so so if we look in the brain, we are not going to find a CPU, we're not going to find memory, we're not going to find instructions, we're not going to find any of that stuff. So um, this concept of computation really has virtually nothing to do with our brain. So what do we find when we look in the brain? Something like that. This is just a whole bunch of neurons all tied together. I think this is a very old diagram made by Golgi, who was one of the first people who kind of imaged what neurons and synaptic connections, et cetera, looked like. But that's just kind of a mess. Of course, it's easier to start out with pulling each one of those neurons apart and looking at each one individually and how they connect. So that's basically the idea of what a neuron is. You've got you've got a cell body, which basically is the mechanics of putting together what I'm going to describe next. Um, it's got these dendrites and dendritic branches that come off of it. Those can be thought of as inputs. And this long thing coming out is an axon, and that can be thought of as an output. And the axon connects to dendrites of other neurons. So this little green guy on the right is supposed to represent another one of these neurons. So basically, you've got this guy is going to get inputs off of its dendrites. It's going to it perhaps may be excited by those inputs, and if it's excited enough, it will send an impulse down the axon, and through these synapses affect other um, neurons downstream. The main things that affect all this are, number one, how tightly these things are connected. So this axon may be tied to several different neurons downstream, and it may be tied to them with different strengths. So this axon may be tied to one neuron with several different connections, so that virtually any kind of impulse that goes down this axon is going to be felt strongly by the downstream neuron. Or it might be a very loose connection, and it might barely affect the downstream neuron at all. Or it can even be an inhibitory connection, which would actually, if something goes down this axon from this neuron, the next neuron might actually be inhibited from being excited by that impulse. So that's the basic thing that's going on in our brain. I mean, we've got all these neurons, and it's this very simple idea of these impulses coming in on the dendrites, and if there's enough of an impulse coming in, it will send out an impulse. And there's also timing involved, so that, for example, if there are lots of rapid impulses coming in, then there will be more likelihood of an impulse or multiple impulses going out on the axon. So you can think of the cell as kind of connecting all this incoming excitement, and if there's enough excitement, then it gets excited and sends something downstream. Okay, the one interesting factor here is the amount of time this takes. This takes about a millisecond, or a thousandth of a second, from the time that these impulses come in on the dendrites to the time that the neuron sends the output down the axon to the next neuron. And we already know that to recognize a human face, for example, takes us about a tenth of a second. And that means there's only about time for 100 of these neurons in a sequence to fire for us to recognize a human face. And obviously, that's a lot. I mean, recognizing a human face is a very complex thing to do, as we know from the fact that we've had so much difficulty coding it in traditional computation. So it seems very surprising that we could do that with only 100 of these neurons firing. And of course, it's not just 100 neurons, it's thousands of sequences of 100 neurons. So there's lots of branching going on, etc. So from beginning to end, yes, there's only 100 neurons from the beginning to the end, but there are thousands and perhaps even millions of neurons going in parallel, all at the same time. And so how can that work? I mean, it's an amazing thing. Of course, a millisecond is absolutely nothing compared with the speed of current computers. And yet, with current computers, we're not getting anywhere near what we did here. So, about the history of all this, and I'm not expecting you can necessarily see all of this timeline, but in 1943 is when McCulloch Pitt originally wrote a paper or book on neural networks, on how these things worked. And they came up with kind of a simplistic model of how neurons might be interacting. And maybe we could get some interesting stuff out of that. And it was just slightly after that Alan Turing was coming up with his model of computation around 46. And so basically, that is an era where we were looking for ways to move forward with computation. And like one branch was looking at the brain and saying, maybe that's how we can do it. And then Alan Turing was looking at this very simple model of computation where you followed all these steps, etc. And of course, the Alan Turing approach got to be successful. So the ENIAC, by the early 50s, we were starting to get some electronic digital computers that were actually being useful. In 1958, which is shortly after that, a guy named Rosenblatt wrote a paper about perceptrons, which was a pretty good, so it was a more refined version of this version that McCulloch and Pitt had come up with. It was a better model of how the neuron worked. And people got excited about that. People, even back then, started talking about, well, gee, maybe we will be able to make machines that can understand humans, that can translate languages, that can recognize pictures. I mean, this really stimulated people's imaginations, and it looked like things might go well until 1969. Two researchers named Marvin Minsky and Seymour Papert wrote a book where they looked very carefully at these perceptrons that Rosenblatt had come up with, and they said, no, they're not going to work. They can't do even some very simple operations that virtually any computer should be able to do. They highlighted the XOR problem, and I won't define that, but you can think of it as an exclusive OR. It's, if this is true and that's not true, then, well, I won't go into it. I'll just say it's a very simple operation, and they proved that a perceptron, at least a single perceptron, which perceptron is Rosenblatt's name for one of these artificial neurons, it can't solve this problem. So basically, Minsky and Papert, by the way, are cutting edge researchers. They were very famous. They became very famous, at least, in artificial intelligence. And people trusted them and said, oh, well, I guess this branch is a dead end. Why should we pay much attention to that? Especially now that we've got digital computers, and they're constantly getting faster and smaller and whatever. By the early 70s, we had microprocessors. You know, why should we mess with all of this artificial neural net stuff? So it kind of went to the back burner. Not many people heard about it. And in fact, so I've been in computing since 1972. I've been programming since I was in early high school. And I never heard anything about this other branch of computing until, so during this time, there was still a contingent, such as at Stanford, that was looking into what could be done with this approach. And Hopfield networks, you'll hear about names like John Hopfield or Jeff Hinton or Terry Sadowski or David Rumelhart. So these people were all continuing to work on this, even though microprocessors were just going like crazy. Everybody was pretty happy with those. And that's where I came into all this. I happened to take a class in 1988 at the Oregon Graduate Institute from Dan Hammerstrom. And it was called Artificial Neural Networks, and we used a book called Parallel Distributed Processing. It didn't even have the word neural networks anywhere in it. And I learned some of the stuff that I'm going to tell you about now, and it seemed really interesting. So that was in 1988 or 89, and it seemed very promising, but still, even after I got out of grad school, I saw nothing happening along these lines. I said, cool class, you know, that's really neat. And it's apparently still a dead end. Um, and then about 10 or 15 years ago, you started seeing things happening. You started getting your phones listening to you and your smart speakers and you know, things, facial recognition and all this kind of stuff happening. So something happened in there. And it is this same technology that happened, but there were some things that actually led it to happening. So what is this technology? What is an artificial neural network and deep learning? So an artificial neural network is basically, here's kind of a very simplistic picture of an artificial neural network, although not that simplistic. They all pretty much consist of an input layer. So each one of these circles represents an artificial neuron. And then what they often call a hidden layer in the middle. And there may be many hidden layers. And in fact, that's where the term deep learning came from, is multiple hidden layers. But I'm going to describe it first with just one hidden layer. And then an output layer. So these are just very simple neurons. And the idea is that each one of these lines represent a connection between this neuron and the neuron at the other end of the line. And each one of these lines has a weight associated with it. And that weight is between 1 and -1. And it represents how strong the connection is between those two neurons. And if it's negative, it means it's an inhibitory connection, which means if there's an impulse coming down here, it actually keeps this neuron from firing, or at least subtracts the chance that it's going to fire. And so these lines very much represent the same as those axons and dendrites and the connections between them. So the way that these, and then the same thing is happening again between this hidden layer and the output layer. And the operation that takes place is that, well, we'll go to the next. So this is one of these neurons, and these are the lines coming into the neuron. So each line has a weight on it. And so some impulse comes down the line, it gets multiplied by the weight on that line, and then it gets compared with a B bias or threshold for that neuron. And if the sum of these weights times the signals is greater than the bias, then this can be considered to have fired or produce an output. And really, that's all there is that's happening in this thing. So here's an example of how this all works and why this is useful at all. We just heard some talks from Steve about the senses, and he talked to us about how the tips of our fingers or the back of our retina or whatever can produce impulses from our environment. Those are the kind of impulses that would go into this input layer. Because this is in a computer, oh, I should kind of, okay. So I told you about what's going on in the brain, and I told you about how computers really work, which isn't anything like the brain. And now we've come up with this model of neural networks. One way to go about this would be, okay, let's start a new industry that develops a new way to produce computers that look just like the human brain and that work like the human brain. That's a whole lot of work. That's kind of a ridiculous amount of work. Instead, we've already got these computers sitting around. That's our hammer. Um, so so now we want this to look like a nail. So we're gonna make our neural networks just be a computer program that runs on a traditional computer, instead of instead of inventing a new kind of machine that works like the human brain. We're just going to simulate this new model that we have on traditional computers. So that's what artificial neural nets has become. So uh, here's the kind of thing that happens. What we'd like to do is take something like a picture of a dog. We'd like to take all the pixels, that is, say the top left corner is dark, so we might put that we'll make a correspondence between every point here on this picture and one of these input neurons. So we'll feed that darker light onto the first neuron, and this darker light onto the second neuron, and this darker light onto this neuron, and etc. So we'll just break that picture of the dog up into individual pixels and throw them onto the input layer. So we've taken this perfectly good picture of a dog and we've split it up into complete nonsense pretty much, and we've feed it onto the input layer. And then this network does what I mentioned before. That is, okay, fine. Whatever number we fed in here that represents that part of the picture gets multiplied by a certain weight and sent to all these other neurons, and all these other neurons get to decide whether or not they're going to fire based on what they got from the input. And then they're going to do the same thing and send their outputs to this output layer. It sounds like complete nonsense. What we want to have happen is we want to associate each one of these output layers with a different thing. So one neuron might represent, this neuron down here might represent dog, but this one might represent a cat. This one might represent a broom. This might represent a flower, etc. What we like is that when we feed in a picture of a dog, the output neuron for dog lights up. And when we fit in a picture of a flower, then the flower neuron lights up. That's ridiculous. How can that happen? Well, it turns out we can make it happen. The way we make it happen is we just start with random biases and weights for all these things. We just kind of mix the whole thing up. We just say it's all random. Then we put in a picture of a dog. It of course makes pure garbage on the output. But then we use a technique called backpropagation to say, we wanted this neuron to light up, and we can go back and slightly adjust all of the weights and all of the biases so that the next time this comes in, there will be a slightly higher chance that this neuron will light up and the rest of them won't. And then we feed in another picture of a different dog, and we do the same thing. And we feed in lots of pictures of different dogs, and we do the same thing. We use this backpropagation to say, no, I wanted this neuron to light up. And then we feed in some cats, and then we feed in some flowers, and then we feed in some brooms, etc. And we do the same thing. For every picture we feed in, we say, this is the neuron I wanted to light up. And based on that, I'm going to go adjust all these weights and biases a little bit. And it turns out that if you keep feeding and you may have to feed the same picture of the same dog through here 30 or 50 times, as well as all the other dogs and other cats and other whatevers. But by the time you do all that, you've trained this network and it will do the right thing. It will light up just the neuron that associates with the picture that you fed in. Okay, well, that's pretty interesting. But why couldn't you just make a big table and say, whenever this picture comes in, produce this output? Well, this is the interesting part. Now I can feed in a picture of a dog it has never seen before, and it will light up the neuron that says dog. It will recognize dogs based on the examples that I've given it of dogs and cats and brooms and flowers, etc. Now, that's overstating the case a little bit. It doesn't do a fantastic job of recognizing, at least with a one-layer network like this, but it does way better than chance at recognizing other pictures that come in. Okay, so that's pretty amazing. Um, and that's kind of the whole start of what this artificial neural net stuff is about. All of this recognition of things, and so it turns out what's happening to some extent is that this middle layer is representing features that are recognized. So for example, it might be that flowers in general are not brown. So one of these neurons in the middle might start representing whether or not this is a dog-like color in the picture or whether it's a flower-like color in the picture. But we didn't tell it to do that. That just comes out of it naturally. It just kind of naturally starts picking features out, and like whether there's something that looks like a nose or ears or the right color, or so so it can actually be trained to recognize things that we don't even know how it's recognizing them. We just feed it lots of examples and it figures out how to recognize it. So that's kind of a good example of what goes on in our brains in some ways. Okay. So what are some general implications of all this? Well, first of all, in order to train one of these networks, you need lots of data, and you need to tell it, you need to not only have data to feed in on the input, you need to tell it, you need to know what the right answer is on the output. So where are you going to get all that data? Well, one way is supervised, and that is just like that picture of the dog. That is actually having someone label, oh, that's a dog in the picture, and therefore we're going to look for dog on the output. And I'll give you an example of some of that stuff in the next slide. But some stuff you don't have to do that so much. For example, if you're playing a game, you already know that a good move is something that leads to you winning the game. So as long as you can recognize winning the game, then you can work backward from that and determine whether or not the moves that led up to it were good moves or bad moves. So if you fed a chessboard in on the inputs and it told you which move to make on the outputs, now you can start classifying whether that's a good move or not a good move based on whether or not it leads to winning a game. Predicting future behavior from past. And this is the kind of thing that people are worried about with Facebook and Google, etc. They want to predict what you are going to do. If they can train a network to behave the way that you behave, then they can guess how you will behave when they put certain things on the screen, like certain advertisements, whether you will click on them or not. So they've collected tons and tons and tons of data of how people react when they throw certain things on the screen. And therefore they have both the input for that neural network and the output. That is how people reacted to that input. And based on that, they can guess how people will react in the future. So that is something that these neural networks are really being used for. Um, Another example is an autoencoder where, for example, if you put the picture of the dog on the input and then on the output, instead of asking for a dog, just one to light up with the dog, you make the output layer be just like the input layer. That is, you want it to recreate a dog by going through this network. Now, this is one thing I should mention. The hidden layer in one of these networks is almost always much smaller than the input layer or the output layer. That means that the network basically has to generalize. That's why it finds these features. It has to find features because it cannot just represent the entire input on the hidden layer. So if you make the output layer the same as the input layer and it has to shuffle, it has to siphon through this hidden layer that's smaller, then it can just find, it can automatically force it to find features, basically. I won't go too deep into that. Another implication here is once the training is over, the learning is over. That is, I told you how to do all this back propagation to change all the weights and the biases. But just a moment. Then once you go out and start trying to recognize things, like you put in a new picture of a dog and maybe it gets it right, but maybe it gets it wrong. At least with traditional approaches, your learning is over. You just now have the wrong answer, and oh well, we can't help, we can't move forward from there. That's very different from humans, where we're constantly learning from our mistakes, for example. And nobody knows how well it will do on any specific input. I mean, if you give it a new input it's never seen before, yes, it might very well recognize it, but if it doesn't, it doesn't. This kind of this neural network is now a big black box, and you don't really know how well it's going to do, or how it's going to do on any particular input. So by the way, suppose it gets the wrong answer. Who do you blame? Who do you blame that it got the wrong answer? Is it the person who was training it that didn't train it enough, but maybe they trained it enough according to the literature and it still got the wrong answer? Do you blame it? It's the blame, at least in traditional computer programming, somebody is writing down all these instructions and it's following them. And if it gets the wrong answer, you can blame the person who wrote the instructions down. But here, there are no real instructions. It's just learning from patterns. Okay, so one question is, how did we make so much advancement over the last 10 or 15 years on this? And why did it take that long to start making those advancements? Well, one thing somebody came up with is this image, and I can't even see the top of my screen, so you know better what it says than I do. But but it's this basically a contest. There it is, ImageNet Large Scale Visual Recognition Challenge. So it's basically a big contest that somebody put together. It says, we've got a huge database of 10 million pictures. And we have gotten a bunch of students and we paid people and whatever else was required to go out there and label every single picture with what's in the picture. And we are going to make a contest where you come up, where you can use any technique you want, but we presume you'll use neural networks, but you don't have to. and to recognize what's in these pictures. And we will give you, I think it's 200,000 or a million pictures, or maybe it's more than that, to train your network on. So we'll give you the picture, we'll tell you what the right answer is on those. And then we're going to give you, 20,000, and you have to tell us, your neural network has to tell us what it thinks is in that picture. And when this started in 2010, they were getting, a little bit better than chance, but I think it was around 15% correct on the answers. And 15% correct is pretty good, because there were like 10,000 different categories of objects in those pictures. So it's not bad. But especially around 2012, um, things took off. And that's when some people started coming up with some extra good techniques. And I'll mention a few of those in the next slide. And by 2017 or so, the recognition was up into the 80% or so. And now these neural networks can do about as good as humans in recognizing what's in these pictures. So what caused all this explosion in progress? Well, some of it was techniques that they came up with. So recurrent neural networks, that's when you have a sequence of things and you want to figure out what's the next thing in the sequence. So you're going to teach it sequences. And you see those all the time nowadays when you're typing, when you're texting, when you're doing any kind of typing. Often it will be guessing what the next word that you want to type is. And that's exactly what type of thing a recurrent neural network does. It basically sets up a neural network where each step in the neural network is basing on all the stuff that came before it. And effectively, it's like adding it's like a very many layered neural network with lots of hidden layers. Another approach is called convolutional neural nets, and that means looking all over, like in a big image, looking in little pieces all over the big image to recognize smaller features in the big image. And you can kind of think about that like when you're looking at something, you don't necessarily take in the entire view of everything you see and recognize everything at once. Your eye kind of scans around your environment and you can focus on things and recognize things in different places. The main difference with convolutional neural network is all of those recognitions can happen at one time. So it can recognize a soup can in this part of my vision and a book in this part of my vision, etc. And that can also be used to recognize faces and things. I recognize an eye here and an eye here and a mouth there, and all that stuff comes together in the next layer to recognize a face. And one of the latest things that's really gaining a lot of attention is generative adversarial networks, or GANs, and that's not what you'll hear about in the news stories. You'll hear about deep fakes. So what a deep fake is two neural networks that are competing with each other. One is trying to fake out the other one. One is trying to simulate something that doesn't exist. And the other one is trying to recognize that this doesn't look right. This does not look like a real picture. So for example, one of them might create a face of somebody that doesn't really exist. So it will put glasses on them and, hair and whatever, and a certain expression. And the next one will look at it and say, oh, no, no, no. I see the glasses, the refraction is different in the two eyes, and therefore, that's not a real picture. And it goes back to the first one, says, oh, well, in that case, I'll fix that. And it fixes it so that second one is faked out. And so these are fighting against each other to the point that once the second one is faked out, then the image that's created is so realistic that humans generally cannot tell that it's a false image. So there are websites you can go to that will create a new face every time you go to the website, and it's a face of someone who doesn't exist at all, and it looks absolutely realistic. There are videos of people, and this includes, Obama or or other people just speaking and saying things that they've never said or that they never will say, and it looks totally realistic. So some people are very worried about this technology and what it could do to um, politics, etc. Some people aren't worried at all. It's really interesting to look at the kind of, and I must say, AI in general. Of course, some people are worried like crazy, and there have been lots of publicity lately about uh, Elon Musk and for example, saying how the AI could take over the world, but other people aren't. I think Bill Gates is on the not worried side, if I remember correctly. A lot of people just don't understand where the motivation to take over the planet would come from, um, but this is the kind of stuff that leads to all this speculation. So another reason that this exploded is we're now awash in data. That is, with Facebook and Google and those people collecting all this data, there and medical, the medical industry. So now we have electronic medical records. We have all of these, digitized X-rays, and we have all of the doctor's results into the electronic medical records. There's all this data that can be used to train these networks. And so all of this stuff can be seen as good or bad. So for Facebook, Google, etc., they have all these records of your behavior. They can train these networks to see how you will behave when they throw various things up on the screen. And so if their goal is to make money off of advertising, then you are just kind of a pawn. They're just getting you to behave a certain way for them to make money. And some people don't like that idea. For electronic medical records, for example, analyzing X-rays is now computers, these neural networks can do that as well as or better than people in many cases. So it can see an X-ray and determine whether there's cancer in that breast X-ray, for example, better than a human can determine that sort of thing. There and going further, just entering a list of symptoms and other things that's happening to this human. The computer has seen all of these charts and what the eventual outcome was when all of these symptoms were present in the past, and can now see a pattern and say, well, maybe you should look into this diagnosis to the doctor. So, how can that be seen as a problem? There's lots of good and lots of scary in a lot of this. Another reason that this has really taken off over the last decade or two, compute cycles. There used to be, you had to go out and search for compute cycles or pay for compute cycles, and now it's like they're everywhere. And you can actually go to websites and just build a neural network and run it for free, I think, these days. And it's you don't even worry about having to pay for any of that stuff. So it's not only free cycles, it's also free software tools. Um, to write a neural network program these days only takes like 4 lines of code. You just say, I want an input layer that looks like this. I want a hidden layer that looks like this. It's a convolutional neural net. I produce the output layer that looks like this. And I want you to feed it the input from this data source and train it this way. And that's pretty much your entire program, because it's all set up in a tool set. So that means lots of experimentation can happen. People don't have to worry about all of the low level details. They can just get on to the high level research. And of course, there's money to be made, especially places like Facebook and Google can make money off of advertising and all that. And not to mention automation in general. I mean, the whole idea behind AI and automation and machinery and this argument's been going on for centuries, and that is, machines taking over from humans, and what are humans going to do, and how are humans going to earn money if the machine can do all the work. And it's the same questions going on now, only now we've got doctors being replaced and drivers being replaced and everything else, instead of just the guy with the shovel or whatever being replaced. So how and where are these being used? So when I took that course in 1988, we were just starting to play with examples of trying to recognize zip codes on mail. So at that time, people were even recognizing zip codes. I mean, to sort the mail was going in front of a person. The person was looking at the zip code, hitting a button, and it would go off in one direction or other. And as far as the rest of the address, forget about that until it got to the right address. And then somebody else would look at the address and deliver it to the right place. Now, of course, we've got, I mean, these computers are reading the entire address and doing all the routing and everything all by themselves. Of course, voice recognition, when I, in the same class in 1988, the research groups at Oregon Graduate Institute were trying to figure out whether they could recognize spoken digits over the phone. And of course, for credit card numbers, et cetera. And of course, now we're talking to our phones and they're answering us. If I was to say, hey Siri, what is deep learning? And
sorry, I missed that. Could you say it again, please?
Hey Siri, what is deep learning?
Deep learning is part of a broader family of machine learning methods based on artificial neural networks with representation learning. Learning can be supervised, semi-supervised, or unsupervised.
So anyway, yeah, so these machines are, at our disposal. And of course, right now on our screen, we're seeing it transcribing everything I say, and it's recognizing all that. It's taking it all in context. That's that's using some of these techniques that I've mentioned. So as far as ATMs, I mean, we couldn't be writing checks and putting them into the ATMs if it didn't recognize all that stuff. Voting is recognizing our signatures and ensuring those are correct. Vision for self-driving cars, facial recognition, of course, surveillance, and the Chinese are especially worried about surveillance. There's surveillance all over China, and I really hesitate to point to them and say, oh, they're the surveillance state. I have a suspicion that there's about as much surveillance here, but um, won't get into that. Voice, of course, you just saw. Images, X-ray analysis, image search. You can do an image search on Google, of course, by feeding in a picture and say, find pictures that look like this. Um, and for medical diagnoses, for influence in advertising. One thing that since the first time I gave this talk, I've realized that um, the term algorithm has become very, very confusing. That is, I started by saying algorithms are one thing and this is something else. These days, the term algorithm has become the thing that, oh, sure, just a moment. The so
Sorry.
like when you're on Netflix and it's recommending which movie you might want to watch next based on the movies you've watched so far, the current lingo is that that's the algorithm that's recommending those things. Well, it's actually more like a neural network that's representing those things, which I just kind of uh, gave as an alternative to what algorithms are. So the term algorithm has been redefined now to be what the neural network recommends. And as far as more far out examples, they've got artificial intelligence now that's based on neural nets that will write a web design. You can just basically say, I want a web page that has this sort of image and that will take this sort of input and that will produce this sort of output, and it'll produce a web page for you. You can say, give me some poetry about this that's in the style of that, and it'll do that. Deep fakes, I already told you about how you can make almost anyone say or do anything. One of the places apparently that this has really been a problem is that in the porn industry, um, they will take some picture of some perfectly innocent high school girl, very pretty face maybe, and they'll put her face onto a porn actress in a porn scene. And this is very upsetting to the person whose face gets put there. Um, it's just our data can be used in new ways that we have very little control over. Um, there's an example where the an AI can actually do uh, debate with you. That you can name the topic, and it will come up with a complete line of reasoning, and you tell it which side of the debate it has to take, and it will come up with a great argument. Of course, Jeopardy gave an example of Deep Blue AI a while ago, and a lot of this debating and Jeopardy and that sort of thing is also based on just the web. The web is a huge data resource, and by just doing a scan of what's on the web, you can come up with the basic outline and the basic content, and then the AI can be used to kind of put that into better forms of communication and deciding what's relevant. And because of deep learning, computers are now world champions at virtually every board game, and that's an example of one of these things where it can play itself. You don't have to train it. You don't have to tell it, oh, that was a good move. You just have to let it play itself forever, and it'll figure out which games are winners and which games aren't. And so, you know, humans, I don't think humans are competing in almost any game anymore. That the computer is it. So have we built a brain? Okay, this was modeled after brains, and it's seems like we're getting there, but this is absolutely not a brain. I should mention, I mentioned exascale computing and earlier with computers, and some people say that that's the level of computing that we need to simulate the brain. But just think back again. These neurons are taking a millisecond to compute. And why do we need an exascale computer, a billion operations per second, in order to do what our brain is doing with only 100 neurons in a row? So it's this is definitely not a brain. We're currently using the same old clumsy computer hardware to perform a simple simulation of these things. By the way, there is something called the Brain Project or something like that, where they're trying to simulate every single neuron in the brain absolutely accurately and try to see if they can get some more insights that way. Brain takes about 12 watts of power to run. One of these exascale computers can take megawatts of power to run. Um, Computer processor, like I said, performs 1 million calculations in the time it takes one neuron to fire, yet a CPU can't come anywhere close to what the brain is doing. And right now, learning in these networks is very clumsy. You just have to give it this by rote, just a ton of examples, and just have it, and then have it generalize on the new data. Um, Societal downsides, I just mentioned, automation always favors capital over labor, and this is a form of automation. And so some people will say it'll increase the divide between the haves and have-nots. Deep learning favors those with the data, and of course that's places like Google and Facebook and whatever, they have the data. The guy on the street doesn't have the data. This technology even lessens the importance of programming. Even programmers may be put out of jobs by this technology. If you're a determinist and think that there's no free will, you can think of that the computer is basically modeling you, and it can guess what you're going to do. And I've heard Eric, who was the CEO of Google, basically saying, "Yeah, we know what you're going to do before you do it." He's perfectly comfortable with that concept. Um, I could have made a whole hour of examples. I thought about doing that. But when I wrote the talk, I figured it was more important to get the concepts across. Uh, there, there, there are a ton of good examples online, and they're lots of fun to look at. Um, and I said I provided a companion document. I still plan to do that, but I haven't done it yet. So anyway, that's that. Thank you.
That was pretty cool. Thanks, David.
Absolutely.
Good.
David Thompson here. Could I take you back to the little black box, and with on my right there were the outputs, and it would say dog, or it wouldn't say dog.
Yeah.
So if it didn't say dog, some mysterious person would go back and tweak the weights of the different inputs. How do you do that? What were they doing? Who did that? And how did they do it?
Yeah. So in this class I took, they explained what the science was behind going back and adjusting the weights. So remember, this is just a computer simulation, and going back and adjusting the weights is no magic. You just change some values in memory. But figuring out what you change the weights to and how you tweak the weights is very, complex math. There's a lot of differential equations and other stuff in there that I must admit I never fully understood. But the that's this book that we used, which was called Parallel Distributed Processing, was just a thick book that half of it I think was math about how they came up with the methods of doing that. The tricky part is, you know, you would think, well, fine, we'll just adjust all the weights so that it will produce dog when I give it this input. Well, it's not that simple, because you have to take into account every single picture that's going to come in. So you just have to adjust all the weights and biases just a little bit for each picture. And then by the time it's seen every picture dozens and dozens of times, finally the weights will be where it can accommodate all of them at one time.
Yeah, this is very interesting to me, David, because a long time ago, when crystallographers started to solve organic structures, there's something called the phase problem. Crystallography focused initially on structures that had what are called heavy atoms in them, because the heavy atoms sort of overwhelmed the phase problem, and you didn't have to make many guesses about what the phases were in order to fit a structure to the data you collected. But in the case of organic structures, you had to make a million guesses and do it cyclically until finally you came up with a structure that fit all of the data. And we're talking about doing this in Fourier space. So this is a pretty complicated math problem. And it took a pretty big computer before we were able to do this on a regular basis, like solving protein structures and things like that. And so it's interesting because this technique of training is very reminiscent, except the computer programs we had to solve the phase program did the automatic learning aspect and adjusted all of the weights, which is exactly what was happening to solve the phase problem. You adjusted the weights of the individual atoms as far as where they were in three-dimensional space. And eventually you came up with a picture that fit all of the data you collected, where you might have 100,000 spots on a big fancy X-ray. And you know, it took a lot of computing. And so until we had big CDC computers, giant ones, 7600s in those days, you know, filled up half a room, we really couldn't solve those kinds of problems. But it's the same technique, and I never realized it.
Yeah, that does sound very similar.
Yeah, you ought to take a look at that and see if my concept of how that's done is actually similar to how this is done. I'd be interested in that, because I mean, I didn't think of it that way, but now that I've seen what you presented, I'm starting to.
Okay. Yeah.
So how big a computer do you need to do this?
So I know that, for example, so one of the tests, I showed you these still pictures that would go in, and I will stop sharing now. The still pictures that would go in, and people trying to recognize them. Google, I think it was Google, decided to just try to recognize cat videos. And they just started feeding in cat videos and seeing if they could get a network that just recognized when it was a cat video. And they used 16,000 processors for that. And this was, I think this was in 2012.
All right, so this is all parallel processing.
Yes. Oh, yes. All of it is.
All right, so you're in that inside layer is basically a whole lineup of processors.
Yeah, so it's interesting because this is inherently a very parallel thing, the way the brain works. That is, each neuron is only connected to a few other neurons, and they can all be happening at the same time.
Mhm.
But when you put this into a simulation in a traditional computer, virtually the way that they do it, and the way I showed it with the artificial neural network, each of the input layer neurons is virtually connected to every one of the hidden layer, for
Right,
example.
right.
And that takes away a lot of the parallelism. Suddenly it's not just 1 to 1 or 1 to 5, it's like every one to every one. And so there have been companies that have built chips that are made specifically to execute these neural networks, but they're all based on this all-to-all connection, and they all just, it takes so much parallelism away from the potential solution. So yes, there is a lot of parallelism that they're now getting just by using networks of computers. And but yeah, I think there's much more, and I think that's where the convergence is going to start happening between, like I said, it only 100 layers of neurons are executing to get a facial recognition in our brain, and it hardly takes any time at all. I think that's going to happen in computers only when they can stop all this all-to-all connection stuff.
Yeah, well, I'm looking at a phone, and I cannot imagine that a phone is comparable to the 16,000 processors that Google used.
That's well, first of all, when you're doing that recognition over the phone, it is relying on a network of computers in the background. If you don't have a network connection, Siri will say, "Just a moment, hang on."
Ah, okay, so it's going up into the cloud somewhere.
Yes. And the other thing is, even phones these days have at least some parallelism, at least 4 to 16 threads going on at one time.
Okay.
So does this have some relationship in any way to quantum computing?
Well, not really. Yeah, no, there might be a way that you could make some connection, but no, not in what I've reported here.
Uh-huh.
Yeah. That's shooting for that billion times billion kind of computing power.
Let's say, okay, some people think that we're not going to be able to model what's going on in our brain using just this kind of knowledge.
Oh.
They think that there is some quantum stuff going on.
Uh-huh.
And I'll just kind of leave it at that. I won't take a stance. My personal feeling is there probably isn't quantum stuff, but quantum stuff is as real as everything else, so why not?
Yeah, the one thing you said is, I'm not sure is completely true, and that is how many neurons are connected to how many neurons at once.
Yeah.
And I think the answer is a whole hell of a lot more than you suggested.
Right. Yes. Yeah. And yes, I have seen, at least thousands in a picture of 1 to 1,000. But even at that level, it's not every neuron to every neuron. And once you get that every neuron to every neuron, which is what most of these neural networks are modeled as, that just really impacts the amount of parallelism.
Right. Yeah, the brain clearly doesn't work that way, although it does get trained in the same way as the neural net. I mean, most vision, for example, almost any of our senses are associated with years of training the brain.
Yeah.
I mean, kids can't focus on anything. They have to learn to focus, and then they have to have the experience of seeing things and touching them in order to get all of the synapses working and generating.
And
The other thing you talked about was the need for memory in all of this. And I'm not sure I understand why you don't need it.
well, I mean, I'm not sure what you interpreted what I said as saying, but anyway, I think what I said is you're not going to see anything in the brain that looks like memory. The memory is the connections. The connections are the memory.
Right, right.
And that's I think you and I probably agree completely on this, but I probably just didn't state it very clearly.
Yeah, basically there are things like the hypothalamus, which have lots of neurons close together and all connected together. And that's where, for example, emotions are stored.
Yeah.
Right? Or you've got a certain place where all of your knowledge and memory of smells are stored. And those have significantly more connections in a small space
Okay.
than other parts of the brain.
Right. So yeah, what I meant, yeah, I meant to, yeah. So those memories are in the form of those synaptic connections.
Right, in the form of pathways.
Right.
Basically.
Yeah, right. And yeah, there's nothing like a memory that you're going out and fetching out of a place and kind of, but yeah, right. Yes. It's all just in the form of these neurons connected to neurons. It's
right. Now let's flip that. The computing systems, the neural nets, how much memory do they need?
I'm not going to be able to answer that very well. Back when I was doing it, by the way, my project for the class was to take the Intel parallel processor that the school had, which had 64 nodes, and each node was a Intel processor, and then it was in a hypercube arrangement, and I distributed one of these neural networks over the nodes of that, so there was some parallelism going on there. But it was slow as hell.
Yeah.
Just, I mean, once you get all those communications going, it just slows everything down. So it was not impressive. But yeah, so it's just basically a memory for each one of the connections. And the connections are, I mean, the weights. So you've got a bias for every one of the artificial neurons, and you've got a weight for every connection, and the connections are exponential. That is, it's all of the input times all of the hidden. I mean, each to
Okay,
each.
yeah.
And
So
then each to each for the.
so basically what you've got to do is store all of those weights that you're generating and then change them each cycle until you get the answer you want. And then you've got to keep all of those weights somewhere.
Yep.
To refer back to them. Okay. All right. Yeah, that makes sense.
Have you heard any discussion among the AI hardware people about neurotransmitters and calcium channels and membranes and stuff? I mean, how would you ever simulate that?
Yeah. So that's an example of, so these neurons, I talked about them as though there's just this impulse that goes out, and a lot of people think of it as an electrical impulse, but it's actually all of this other kind of stuff going on.
Yeah, stuff actually moves down the axon.
That's right. And the biases are actually by changing the level of certain elements so that the neuron doesn't fire until it reaches another higher.
Yeah. So
level.
they're all voltage gated, basically.
Right. And as far as learning, of course, this back propagation stuff has absolutely nothing to do with the way humans learn in our neural networks. we have these neurotransmitters and stuff that, you know, if something good happened as a result of you know, our action, then maybe we get this hit of, you know, a positive neurotransmitter that solidifies those things that fired that time, and maybe that strengthens the connections that cause that result. And you know, it's a completely different approach.
Yeah.
And,
No, there really is feedback. I mean, think
Yeah.
about a baby
right.
learning how to grab a ball,
Yeah.
right? They don't know where it is at first because they don't know how to use their stereoscopic vision. And so they reach in some direction and they miss it. And so they pull their hand back and they try again. And each of those is the kind of negative feedback that you're talking about. No, it's not a dog. You missed the damn ball, right? Go a little to the left and eventually they get the coordination between where their arm is and what they're seeing stereoscopically.
And,
Learning to play the piano, actually.
and I think that success
Yeah.
results in some neurotransmitter that helps to solidify connections or something.
No, absolutely. Absolutely.
Thank you, David. With that, I will go solidify my connections. Have a really good evening. Thank you so much. It was really super cool.
Absolutely great, David. It was even at the level I could understand it, which I've tried to do that on my own many times. And the books always make it too complicated. They don't simplify it to the point where you can get the basic concept. I'm sure you picked that dog equals dog things out of someplace. But the explanation of that dog to dog thing in the book wasn't good enough for me. Let's do it that way.
Yeah.
So thanks very much. And I'm going to take off too. I think I mentioned to Don that I'm going to try to give part 2 of the Zircon talk next week. I think I should be able to prepare it in time, although I've got some health issues that I've been dealing with, and they're sort of distracting me from working very hard so far. I've tried a little bit today and I started to make progress. So I'll let everybody know in advance if I'm not going to make it. But I'm counting on myself to be able to do it. Anyhow, thanks again, David.
Okay, well,
Good seeing you all.
yeah.
Take care.